afraid to answer questions, but this is just so that I know I have people out in other classes, and y'all are the chosen ones today. Okay? So we're going to learn about macromolecules today. What does macro mean? Big. So we're going to learn about what type of molecules? Big molecules. And every molecule in your body is going to fall, well, most of the molecules in your body are going to fall into two categories, either organic or inorganic. And the ones that fall into the organic category are going to fall into the categories of carbohydrates, lipids, proteins, and nucleic acids. And as we talk about those, we're going to talk about what elements they're made up of, how they're put together, what their functions are, why they're important. And we're going to go through and fill your brain with lots and lots and lots of knowledge. So you're going to leave here going, oh my goodness, what should you go home and do tonight? Look over it. Go home and look over it and start trying to remember information. This unit, or this part of this unit, is very much memorization. But you're going to see this over and over and over again. From now all the way through the end of next semester, we're going to keep referring back to these macromolecules. So the more you learn and remember now, the better off you're going to be come April, because we're going to keep going back to this stuff. Okay? If you have questions, if you don't understand something, you just need to make sure that you ask, because if you have it, I promise somebody else has the same question. But in order to understand macromolecules, we have to get some chemistry basics in. So, first off, reactants yield products. If you flip the page, this should be all like fill in the blank notes for you as you go. How many of you have ever written a chemical equation before? No? Anybody wrote the equation for photosynthesis in environmental science? So tell me the equation for photosynthesis. Somebody start me off. Give me part of it. Okay. Oh. Let me try one more time. What else?
Energy.
Okay, what kind of energy? Okay. So light, energy. What do plants take in from the atmosphere? Oh, I know y'all remember this. Carbon dioxide, so 6 CO2. Is there anything else? Did y'all learn photosynthesis in environmental science? What do we get? Glucose. What's the formula for glucose? Absolutely. Show 6-12-6. And what do plants give off? Oxygen. So this is the chemical equation. My whole point, one, is to get you to remember this equation, but two, where are the reactants? Just say it. Where are the reactants? Is it just this? Is this just the reactant right here? Mm-mm. All of this right here are your reactants. And all of these over here are called your what? Products. How do we read that arrow? Okay, well, when we see it, like if we see that arrow in a food web or something, we're going to think it's a transfer of energy. And we are moving energy from one place to another, so not a bad thought. But when we're reading this, we would say 6 H2O plus light energy plus 6 CO2 yields. Now, if you're driving, what does yield mean? Like slow down, give the other people have right away, right? You're looking before you go. Yields in this case means produces. So the reactants produce the products. The reactants yield the products of glucose and oxygen. And the term catalyst means that it speeds up a reaction. So when you're making spaghetti, you ever made spaghetti noodles? How do you make the spaghetti noodles soft? You put them in water, right? But can you just put them in cold water? You put them in hot water. If you put them in cold water, eventually they're going to get soft. But you're not going to be able to eat it for dinner that night. So how do we make it happen faster? We boil it, right? We add heat. So in that case, heat is a catalyst. Now, in living organisms, heat is never a catalyst. Heat doesn't speed up reactions in our body. We have biological catalysts. Which means speeds up reactions in living organisms, and they are called enzymes. So a catalyst speeds up a reaction, and they're called enzymes in living organisms. So I've introduced some new terms to you. We're going to keep introducing new terms. This is lots and lots of terminology for you. If I need to go back, y'all just need to tell me. If I need to slow down, tell me. There are two types of chemical reactions that you need to make sure you know. Now, when you get to chemistry, they're going to give you lots and lots of other terms for these. They're going to give you lots of other reactions. Right now, we're going to focus on these two. There's a dehydration synthesis or a condensation reaction. What does synthesis mean? I know what synthesis means. Synthesis means to build. What does dehydration mean? Just say it. Okay, if you are suffering from dehydration, you're suffering from lack of water. So we're going to dehydrate something. We're going to do what? We're going to remove water, right? So dehydration synthesis says that we are going to build something by removing water. Good. So we're going to build something by removing water. It's also known as a condensation reaction because anybody ever had a big old cup of sweet tea? It's nice and cold and you walk outside and what forms all over the outside of the cup? Condensation, which are droplets of water that are being removed from the atmosphere. All right. So dehydration synthesis can also be called a condensation reaction. Those terms are used interchangeably. Because what happens is I take this molecule here. I take this molecule here and this molecule here, and I remove a hydrogen from one and a hydroxyl from the other, and I get a water molecule. That's our condensation water droplet. We get one molecule of water, and in the process, we connect these two molecules. So I took two separate molecules, removed the water, opened a place for them to attach to each other, and now they've attached. They're building something bigger. You with me so far? Okay, so let's see if you can do this. Here's my 6 molecules, and I want you to connect them using dehydration synthesis. Don't say it out loud, but how many molecules of water are you going to get when you do that? If you think you know, just raise your hand so I can see how many people think they know. How many molecules of water will you get when you connect those 6 molecules? If you think you know, just raise your hand. I'm not gonna call on you, I just wanna know if you think you know an answer. I have 6 individual molecules and I want to connect them. I want to make one long chain. And to do it, I have to use dehydration synthesis. I want you to know how many molecules of water do you think I'll get? Got 3 people who think they know? 4, 5, 6. Draw it. Connect them. See how many molecules of water you would get. How many of you think you're going to get 6 molecules of water? How many of you think you're going to get 5 molecules of water? Okay. How many of you think you're going to get 7 molecules of water? 8, 4, 9. What are we thinking? Yell out numbers. 3. Okay. Because you did this, right? 1, got a molecule of water. Is that what you're saying? Is that where you got 3 from? But what if I wanted to make it a long chain? I want all of them connected. Means I need to form a bond here, so I have to take out a molecule of water, and I want to form a bond here, so I have to take out a molecule of water. So to connect 6 molecules into one long chain through dehydration synthesis, for every bond that I need to form, I need to get a drop of water. So if I had 1,671 molecules that I needed to connect in one big long chain, how many drops of water would I get? 1,670 molecules of water to connect those, to make a chain, because every bond that forms between them, but here, I'm not connecting it to anything, so I don't need to form a molecule of water. Does that make sense? I like that question. I like to give you big numbers where there's no way you're going to be able to draw all those molecules and figure it out. But if I'm asking you to connect them in a big chain through dehydration synthesis, you get 1 molecule for every bond that you form. So dehydration synthesis, are we building or breaking down? We're building, right? So if we're building something, are we going from something small to something big, or something big to something small? I'm building something, small to big or big to small? Small to big, right? All the little bitty bricks come together to make the house. That's dehydration synthesis. Then we get hydrolysis. Hydrolysis is breaking large molecules into smaller molecules by adding water. Breaking large molecules into small molecules by adding water. What does hydro mean? Hydro means water. Lysis means to split. So we're going to split something by adding water. Does it sound like the reverse of dehydration synthesis? And that's what it is. So I have these molecules that are connected right here. They're connected, and to break this bond, I'm going to add water, and then it's going to be broken. So I go from something bigger to something smaller. Sometimes hydrolysis is talked about as digestion. So in hydrolysis, are we going big to small or small to big? Big to small. We're breaking it down. When we take in our food, when we digest it in our stomachs and in our small intestine, hydrolysis is occurring because we're breaking it down into smaller pieces. So as we're learning about these macromolecules, I want you to ask yourself, what are the small pieces being used to make the big pieces? Because you're going to learn the names of the small pieces, you're going to learn the names of the big pieces. So what are the small pieces that through dehydration synthesis can be put together to make these big pieces, and what are those big pieces? So as we're doing that, I kind of want you to think about putting them together and taking them apart. More terms that we need to understand are types of bonds. So if you remember on Friday, we talked about an atom. We said atoms had subatomic particles called protons, electrons, and neutrons, right? Yes. And those protons, electrons, and neutrons, protons had what charge? Positive. Electrons had negative, and neutrons had neutral. So those electrons we said were involved in types of bonds. And that's how atoms could connect to each other, is through the electrons that floated around those outer orbitals. And we said that water molecules, between the hydrogen and the oxygen, they share electrons, but they share them unequally. So we said water had what type of bond? Polar covalent. Does that ring a bell from what we talked about Thursday and Friday? Okay. So we're going to learn the different types of bonds, but to do that, we're going to have some volunteers come up here. Okay? So I need 2 people to come stand up in the front to help me demonstrate a covalent bond. You get candy. Okay, so stand in the front. Right here and right here. Face the front. We'll face the left. Sorry, you're right. I said it wrong. All right, so these are both atoms. Okay? A-T-O-M-S, not A-D-A-M-S. Atoms. And atoms have electrons that float around in their outer orbital. So hold your hand out. You have 1 electron floating in your outer orbital, and you have 1 electron floating around in your outer orbital. They're both hydrogens. Hydrogens want 2 electrons in their outer orbital to be stable. How many do they each have in their outer orbital right now? 1. So what they can do is these hydrogen atoms can come together and share their electrons. Put it in that. Put it in that. Hold your hand out like this. Put it in this hand. Put your hand out. Now they're sharing their electrons, equidistant from each other. That's a covalent bond. Are they connected? Yeah? With me? They're sharing their electrons. They both have 2 now because they're sharing them. That's a covalent bond. Make sense? Yes? Okay, y'all can take your gum if you want hand sanitizer. It's all around the room. Now I need 2 more volunteers. Oh, I'm going to be calling people. Come on. Thank you. All right. Your oxygen and your hydrogen. They both need electrons to fill their outer orbital to be stable. So what could you do to become stable? You need more electrons. Could you share? Yeah, but watch this. Riley's a little greedy, so hold on to yours. Hold on to it tight. Don't let it take it, but you want to hold on to this one too. Hold on. Come here. Now you hold on to that little big part right there. You start pulling it this way. She's pulling it. Keep pulling. Closer to you, closer to you, closer to you. So look, she's pulling it, and look what's happening to Chloe. She's moving. She's kind of bending. But who's getting most of that electron? Riley is, right? The oxygen, because she's a little greedy. Right? So she's unequally sharing. Hydrogen's holding on for dear life over here, but oxygen's getting most of it. That's a polar covalent bond. Make sense? That's what water does. Okay. Are you going to give it back or be greedy? Okay. Well, I mean, but that's a polar covalent bond. I need 2 more volunteers. Thank you. Who's going to come volunteer with Cam? All right, Abby. Then we have an ionic bond. All right, so Abby is sodium and Cam is chlorine. Chlorine has 7 electrons in its outer shell, and it needs 8 to be stable. And Abby here, sodium, has 1 electron in her outer shell. She needs 8 to be stable. Is it easier for her to give away 1 or find 7 more? Give away 1. What about Cam? Is it easier for her to find 1 or give away 7? Find 1. So here's what happens. Abby, give Cam your... So Cam just got an extra electron. What charge does electron have? Negative. So Cam has a negative charge, but Abby just lost an electron. If you lose a negative attitude, what kind of attitude do you have? Positive. So Abby's positive, Cam's negative. What do we know about opposites? They attract. So now y'all are besties. And you're hanging out, you're walking through the halls together, right? They're just besties. Now, are they holding hands? Do you hold hands with your bestie as you walk down the hall? Probably not. Right? So could I very easily go, Cam, come here, and pull her apart? Could I do that? Yeah, because they're not sharing electrons. They're just kind of attracted to each other, holding on, being besties, right? Think about it. So an ionic bond is where one atom gives the electron to the other one, and then they hang out because they have opposite charges. It creates ions, a positive and a negatively charged atom that are attracted to each other. Make sense? Okay, thank y'all. Here, Cam, you can keep that one since you gave it to you. You can have another one. Okay. Thank y'all, all for the volunteers. So which of these do you think is the strongest? Which one do you think would have been the hardest to separate? We had Will and Leighton here, and they were like connected, sharing electrons, right? Then we had Riley and Chloe. They were connected, but one was holding on for dear life, and the other one had a pretty good grip on that other electron. Then we had two just kind of hanging out next to each other. Which one's easiest to separate? The ionic was the easiest to separate. Which one's probably the hardest to separate? Covalent. So the covalent bond is going to be our strongest, and it decreases in strength as we go this way. Now, on Friday or Thursday, we mentioned another type of bond that's present between 2 different water molecules. Remember, you all have a superpower. You can hold your finger up, put your finger in, and break it. What was that bond? A hydrogen bond. So we're going to add a 4th bond. And it is a weak attraction between molecules. Now these 3 are between atoms, but a hydrogen bond is a weak attraction between whole molecules, like water molecules. Does that make sense? I just realized it's not really working. It's a weak attraction between water molecules. So one water molecule is weakly attracted to another because of those polar covalent bonds and the oppositely charged ends. So of those 4, which one is the easiest to break? The hydrogen bonds. They're the easiest to break. They're the weakest. Do you understand basic idea of the bonds? There's a whole lot more to it. I'm gonna leave it to your chemistry teachers. Covalent equal sharing, polar covalent unequal sharing, ionic transferred electrons, hydrogen bond weak attraction between molecules. We see hydrogen bonds between water molecules, and we'll also talk about them between DNA strands. So that's where you're gonna see hydrogen bonds between DNA and in water. Questions on any of those terms before we keep moving on? I'm gonna keep giving you terms. I feel so excited. Are y'all ever excited? Like, what excites you? Because y'all have perfected this blank stare look. What excites you? The weekend. So Fridays, I can expect lots of energy from y'all. Okay. Maybe we need to have, if weekends excite you, maybe we need to do Saturday school, because then you'd be excited on Saturday.
I thought we were.
Trying. All right. Next terms, organic and inorganic. Remember I said all the molecules in your body are going to be classified into two categories. Organic or inorganic. Now when we think organic, we tend to think like the grocery store, and you have the organic fruit or the not organic fruit. And the organic fruit is grown with all naturally, no pesticides, no chemicals, no synthetic fertilizers, right? All natural. Then we have inorganic, those are the ones that might have had pesticides sprayed on them or use synthetic fertilizer, something to make it not completely natural. But we're going to define these terms differently. Organic, in this case, means it contains carbon and hydrogen. Carbon and hydrogen. Inorganic means it does not contain both carbon and hydrogen. So it can have, if it's inorganic, it can have carbon, but not hydrogen, or it can have hydrogen and not carbon. So where would water fall? Which category would water be in? Say it loud. Inorganic. Because it has hydrogen, but does it have carbon? No. The molecules we're going to talk about today and tomorrow, the macromolecules, they're all organic. So what do you think they have? Carbon and hydrogen. All of them have carbon and hydrogen. And that's why carbon and hydrogen were two of the most common elements in the human body. The other being oxygen, and you'll see that they all the ones we're going to talk about, have oxygen as well. The four categories of organic compounds, these are sometimes called the biomolecules. Four categories of macromolecules, they get referred to all the time. There's carbohydrates, lipids, proteins, and nucleic acids. And at any given point, I'm going to look at you and go, what are the four macromolecules? And I want you to be able to tell me carbohydrates, lipids, proteins, and nucleic acids. Like I said, we're going to come back to these over and over and over again throughout the year. How many of you have heard some of these terms before? Okay, good. Carbohydrates are made out of carbon, hydrogen, and oxygen. Somebody name an example of a carbohydrate that you know of.
Bread.
Okay, bread. Anything else? Pasta. Sugar. Who's going to say sugar? Lipids are made out of carbon, hydrogen, and oxygen. I know what lipids are? What do you think? They're fats. Then we have proteins. They're made out of carbon, hydrogen, oxygen, and nitrogen. Okay, keratin is a protein. When you think protein, what do you think? Meat? Anybody think muscle?
Which is meat.
Which is meat. When you're eating a steak, you're literally eating cow muscle. Nucleic acids are made out of carbon, hydrogen, oxygen, nitrogen, and phosphorus. So if you can remember in this order, carbohydrates, lipids, proteins, nucleic acids, it's cho, cho, chon, chon. Turn it out there. Cho, cho, chon, chon. Have you ever heard that before? Okay. So do you need to know the elements in each of these molecules? Yes. So we're going to go through and we'll actually be repeating that information again. Why? Because you need to know it. This unit, like I said, is lots of memorization. So please, please, please make sure you're studying. More terms. Monomers and polymers. Mono means one. So a monomer is one single subunit, one building block that is used to make something bigger. So if you've ever played with Legos, I loved Legos growing up. I loved it when my kids loved Legos because I got to play with them. Legos, each little individual brick is a monomer. But individually, they're not much. But if you put a bunch of them together, is this one? Hey. Yes, ma'am, I'll send somebody. Okay, bye. All right, guys, I need a couple of people with lots of protein in their arms. They can go pick up a couple buckets of frogs from this first. Mm-hmm. 1, 2, 3, 4. I don't know how many there are. I think there's 2 or 3 or something. If you want to get a rolling cart, you can get a rolling cart out of there, and y'all can help each other lift them up. They're not look, rolling cart. You're gonna get the rolling cart, go to Miss Spur in the front office. I don't think she wants the frogs to stay there very long.
Why are there buckets of frogs?
For dissections.
Oh, are they dead?
They're not alive.
Okay, good. I thought it was like a bucket with live jumping frogs.
No. Okay, so we're recording again. Here we go. So back to terms now. Monomer, little bitty Lego brick, right? Right? So if somebody handed you a Lego brick and said, look what I made for you, you'd be like, you didn't make anything, you just picked up brick, right? But if they put them all together in a castle, then that's pretty cool. So the monomer is that one little brick, but the polymer is a whole bunch of them together. Poly means many or more than one. So as we talk about each of these categories, carbohydrates, lipids, proteins, nucleic acids, we're going to talk about what the monomers are and what the polymers are. When we put those monomers together, what do they build? Does that make sense? Okay. So here's a picture of your monomer. Here's a picture of your polymer. What process was used to take these monomers to build this polymer? Say it. Dehydration synthesis. Y'all agree with that statement? We took a bunch of monomers, put them together. On this picture, from one end to the other, how many molecules of water were made as we formed this? 8 molecules of water, because how many monomers did we put together? 9. So in each of these here, we would have formed 1 molecule of water as that bond formed through dehydration synthesis. If I wanted to break it down into 9 separate monomers, what process would I use? I want to break it down. Hydrolysis. All right, so let's talk carbohydrates. Carbohydrates are sugars and starches. And carbohydrates' main function is a quick source of energy. Main function is a quick source of energy. Anybody ever been around little kids when you give them sugar? What happens to them? They get crazy, they go hyper, right? And they get really, 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 really hyper because we gave them sugar that gave them lots of what? Energy. But do they stay hyper for a long time? No, they're really, really hyper, and then they like pitch this fit because they're coming down off of a sugar high, and then they fall asleep because they don't have a lot of energy anymore. So carbohydrates, their function is quick energy. They are made of carbon, hydrogen, and oxygen in a 1 to 2 to 1 ratio. So that means this. Well, what does carbo make you think? Carbon. And hydrate, what does that make you think of? Water. So it's a carbon and water. See that ratio? Here's your carbon. Here's your water. What's the formula for glucose? C6H12O6. If you have Miss Harper, she would always say CHO, 612-6. Does this match this requirement? Could I reduce those numbers and get 1 to 2 to 1? I take the greatest common factor, I think that's the right math term. Reduce 6 by 6, I get 1. If I reduce 12 by 6, I get 2. So I get the 1 to 2 to 1 ratio. So if you look at carbon, hydrogen, oxygen, then it's in that 1 to 2 to 1 ratio. You know it is a carbohydrate. Now, remember I said we're going to learn monomers and polymers, right? Monomers of carbohydrates are called monosaccharides. What does mono mean? One. And saccharide means sugar. So monosaccharides are one sugar. They're also known as simple sugars. So our monosaccharides are called our simple sugars. Examples are glucose. I think they may be listed on your paper. Fructose, maltose, and galactose. You're right. I apologize. Take maltose off. We have glucose, fructose, galactose. Where do you think fructose might be found? Fruit? Yes? Corn syrup, so from corn. So what type of organism do you think makes fructose? Plants. Do you think we make fructose? No. We don't make fructose. We make glucose. Galactose. Where do you think we might find that? Milk or space. Always get that answer too. But galactose, it's from milk. What type of organisms do you think make galactose? Animals. Okay? So fructose is made by plants. Galactose is made by animals. All living organisms make glucose. If you've ever heard anybody talk about their blood glucose levels, they're talking about those monosaccharides, those glucose molecules that are in their blood. Because no matter what carbohydrates we take in, we're going to break them down and convert them to glucose, because that is how our body can use them, is as glucose. Now, if I'm going to draw a monosaccharide, it's going to be a hexagon. It's going to look like that. This is the actual chemical structure for glucose. But when I draw it, that's a monosaccharide, one single hexagon. So if you see a hexagon, think monosaccharide. Now, are there other monosaccharides? Yes. These are just the most common. Then we have disaccharides. Disaccharides are made up of two sugars. So how do you think we might draw those? Two hexagons. What process are we going to use to put these two hexagons together? Dehydration synthesis. And the bond that's going to form between them, here, that's a covalent bond. Disaccharides. Maltose, sucrose, lactose, where do you think lactose is found? Milk? Anybody ever heard of lactose intolerance? People who are lactose intolerant literally can't digest, they can't break down that bond right there. It's that simple. They literally can't break that bond, so they're lactose intolerant. Now, lactose is made out of glucose and galactose. So lactose is made out of glucose and galactose. Are those both sugars that animals can make, glucose and galactose? Yes. Maltose is made out of glucose and glucose. And sucrose, does anybody know what sucrose is? How many of you have ever used sucrose before? Anybody ever use the white granulated sugar, like to bake, or you put it in your cereal, or you put it in your coffee? Buy it like in 10-pound bags? That's sucrose. Where do we get that sucrose from? Plants, specifically sugarcane, right? Sucrose comes from fructose and glucose. So all of them are made of two monosaccharides that we put together to build a little bit more complex sugar. Is there more? He is. Okay, you're welcome. Bye. Okay. So we have monosaccharides, those are our monomers, one simple sugar. Disaccharides are also classified as simple sugars. Are they a polymer? What does poly mean? Poly means many, right? So these don't actually classify as polymers. They are simple sugars, so but we call them dimers. And you're not going to see that in every category, but I need you to understand disaccharides. Di means two, so it means we're going to have two monomers together. Then we get to polysaccharides. Polysaccharides are complex carbohydrates. So our monosaccharides, disaccharides, simple sugars, polysaccharides are our complex carbohydrates. And it's made up of chains of monosaccharides. So how would I draw this one? A bunch of hexagons together. I'm going to take a bunch of those monosaccharides and connect them. And how I connect them determines which type of polysaccharide. And you don't have to memorize that right now. What process is going to form polysaccharides? The process is going to take a bunch of monosaccharides and put them together into polysaccharides. Dehydration synthesis. We're going to keep going back to that, dehydration synthesis. Now there's 4 types of polysaccharides. There's starch. How many of you have ever heard of starch? Okay. Starch is an energy storage compound in plants. It's an energy storage compound in plants. What things can we eat to get starch? Potatoes, yes. What else? Just yell it out, I don't care. Some fruits, yes. Which is that's what a potato is as well. Corn, bread, wheat, grains, all of those have starches. They're energy storage compounds. Anybody ever had potatoes that were in your pantry and maybe they were in there a little too long? And you pulled one out and it has these white things coming out of it? Those white things, we call them eyes, but they're not really eyes. They don't help them see. But these things coming out of it, it's literally the plant growing because that potato's alive. And so it's starting to grow these eyes out of it so that it can spread and reach water and it can multiply. But if you get one and it has these eyes coming out of it, what you'll notice is the potato's starting to get kind of squishy. Because guess what is being used in the potato? The energy that is stored in the starch, the white stuff that we like to eat that makes a potato, you have some cheese and some butter and some sour cream and bacon and all that fun stuff and makes it really yummy. That white stuff is starch. Well, it's storing energy. So as the potato grows, the starch gets broken down and used for energy. So it's getting squishy because not all the starch is there. It's getting used for the potato to grow. And if it sits there long enough, it's going to get really squishy because all that starch is going to get used up. So we have starch, which is energy storage in plants. Then we have glycogen, which is energy storage in animals. And we find glycogen in the muscles, in the liver, in animals. So if you're exercising, your muscles are contracting and they need what? What do your muscles need? Energy, right? So the first place they go is the glycogen that's stored in your muscle. Because it's quick energy, it's easy to break down, they get it real fast. Then it uses the glycogen in your liver. And then once that's done, it uses any glucose from your blood. And then after that, it goes to fats. So they say if you're trying to lose weight and you're exercising, you want to exercise for more than 30 minutes because you have about a 30-minute glycogen storage worth of energy. After that is when your body will go to start using energy stored in fats. When you eat, your body will replace the energy in glycogen first, or it will store the energy as glycogen first, then it will store it as fats. So it's a short-term energy storage. It's doesn't store a lot of energy, it just stores enough to just kind of supply. It stores enough for the fight or flight syndrome. You know what that is? You're in a high stress situation, your adrenaline gets pumping, and your body responds. It needs a lot of energy to do that. The amount of glycogen you have is supposed to be enough to fuel that fight or flight response. And then after that, your body tends to drop out of that fight or flight response. So these are both energy storage. Then we have cellulose, not cellulite. You hear somebody talking about cellulite, they're talking about something different. Cellulose is a structural component in plant cell walls. Humans I don't know what just happened. Humans can't digest it. So, you know when you eat popcorn and the stuff that gets stuck in your teeth, the kernels? That is cellulose, the outer covering of our corn kernel. The outer covering of a green pea, cellulose. Anybody ever taken a bite of celery? It has those stringy things sticking up? Cellulose. We can't digest that. What that means is, however it comes in, it goes out the same way.
So it can't take anything from it, any energy at all?
Not from cellulose. We can't digest it. Now, cows can. Certain animals can. Humans cannot. We don't have the enzymes necessary to do it. So if your parents make you eat certain vegetables, let's say green peas, and you hate green peas because they just taste awful. So you're like, well, I'll just put it in my mouth and use some water and swallow them like medicine. Guess what, guys? You have gotten 0 nutrients from that green pea because your body can't do anything with it. It can't break through that cellulose, that outer covering. And it comes out exactly how it goes in. This is what we call dietary fiber. So it's still important to have in your diet. Anybody ever heard anybody talk about fiber, increasing the fiber in your diet? A lot of times people as they get older tend to increase the amount of fiber because your body can't digest it, so it literally just pushes it through your digestive tract. So it helps keep people regular. That's Puka's biology, so it's okay. Anybody have food packets with them? Like a packet of food that has the ingredients? Take it out, look at it. If you have like snack for later or for lunch and it's like a bag of chips or a protein bar and it has the ingredients listed, I just want you to see it. Y'all all stared at me like, is this a trick? Is she about to take my food? I didn't eat breakfast, so valid thought. But I'm not going to steal your food. I just want you to look at it. I'm not going to gross you out to where you don't want to eat your food anymore. I'll save that for another day.
Oh, nothing is not
Those flaming hot Cheetos?
Yes.
You know those create ulcers?
No, yeah.
You should not eat flaming hot stuff for Takis or anything else. But that's just a personal opinion. But look at your ingredients. First of all, you should see something that says calories. Right? And it gives you a number. That's the amount of energy you're going to get from that food. That's what calories is, a measure of energy that food can provide you with.
Energies and like 170 energies. Like,
no, calories. Calories a unit. Calories is a measurement of energy. And on your food, let's say it says there's 220 calories or calories on there. It should be written with a capital C, right? See the capital C? What that really means is it's 220 kilocalories. So if you want to blow somebody's mind who keeps up with calories, when you eat that bag of chips, that's 220 capital C calories. It's really 220,000 little c calories. But counting calories would be way too hard if we counted by the thousands. So they do capital C calories, but it means kilocalories. But that's how much energy you can get from that food. An average adult burns about 2,000 calories a day. So people who are counting calories, they're burning 2,000, they're trying not to take any more than 2,000 in. Or if they're trying to gain mass, they may take in more than that because they want to be able to store some. But 220 calories for the bag of chips, that's the amount of energy that you have. Then if you look at carbohydrates, see carbohydrates on there, and it tells you how many grams. Then they break the carbohydrates down into sugars. The sugars, that's the measure, that's how many mono and disaccharides are in there, the simple sugars. Those are the ones you're going to digest first, you're going to get the immediate energy from. Then it says, probably doesn't list starch on there. Any of yours list starch? But it probably says dietary fiber. You see dietary fiber on there? That's how many calories of carbohydrates that you can't digest. That's what it's talking about on there. You can't digest it. How much cellulose is in it, or how much chitin. So our fourth type of polysaccharide is chitin. If you want to eat your snack, you can. You just have to separate it. Or you can put it up. But chitin is our fourth polysaccharide, and it's also structural. So cellulose is structural in plants. Chitin is structural in cell walls of fungus. Name a fungus that we eat. Mushrooms. But guys, we can't digest the cell walls of mushrooms either. We can't digest chitin either.
So why do we eat these things that we can't digest?
Because there's other parts of it that we can. We just can't digest the chitin that's in the cell walls, but we can chew it up and break it down. So like when you chew up corn, you can't digest the cellulose, but you can break it. So where we're getting the sugars and starches from inside of it. So chitin is in fungus, and it's also in the exoskeleton of arthropods. Arthropods include our crustaceans like shrimp, crawfish. They include insects. Anybody ever stepped on a cockroach, and when you step on it in a really quiet room, you hear, right? When you step on a bug and you hear that crunch, you're literally crushing its exoskeleton that's made of chitin. When you peel a crawfish, the shell that you're taking off of it, chitin. Don't eat the shell.
So how hard is that compared to like regular bone in terms of their size? Like, I feel like the only reason we're able to crush it is because we're so much bigger than them. How hard it is. It's so big.
It's pretty equivalent to what bone is for us in our size. But we can't digest that exoskeleton. So don't eat the shell of the crawfish. It's not good for you. But chitin is structural for fungus, and arthropods, cellulose structural for plants. Feeling okay? All of these are a bunch of monosaccharides put together to make something bigger. So this is just showing you, do y'all have this picture? No? Okay. So if you look at the picture, it's just showing you the different type of polysaccharides. So here's starch. You can see all the little hexagons here attached. Then we have glycogen, a bunch of little hexagons, just in a different form. The way they attach determines what they are. You don't have to memorize their structure, but just you see all of the monosaccharides connected together to make these big polysaccharides. And depending on how they're attached, determines how we can break them down. Notice how cellulose and chitin look very similar. See the similarities? We can't break those down, but we can break these down, and notice how they kind of look similar in their structure. And you'll learn more about that next semester. For right now, that's what you need. All good so far? Am I blowing your brains? No? Good? Ready for more information? Blank stares. Keep going. I had one person who said they were getting lots of information. Carbohydrates have properties that say they are polar. What other molecule do we learn is polar? Water. Well, remember this, when you get to chemistry, he's going to say that's not always the case. But if you can remember that like dissolves like, polar molecules will dissolve polar molecules, or not necessarily dissolve, but will attract polar molecules. That also goes for ionic, anything with a charge. So, does sugar dissolve in water? Yes. If you put bread in water, does it take up the water? It does, because it's not afraid of water, it doesn't repel water, it's not waterproof. It will take in that water because it is polar. So carbohydrates are polar and attract water. Now let's talk lipids. Lipids are fats, oils, and waxes. And they have lots of different functions. Fats store energy. They're long-term energy storage. And can also store more energy per gram. So if you look at the food label, if you were to look at it, you would see where it says calories and it says calories from fat. Because fat can store more calories per gram than carbohydrates. Carbohydrates store about 4 calories per gram. And lipids store between 7 and 9 calories per gram. Then we have waxes, which are used to produce waterproof coverings. We don't produce waxes. Anybody think of an animal that does produce waxes? Bees produce wax. Lots of plants produce wax. If you look at leaves and they're really, really shiny, you take one of those leaves and you take your fingernail and scrape off the top, you'll literally scrape off what looks like if you were to scrape your fingernail on a candle. You'll just scrape off a layer of wax, and it's there to prevent water loss. Then we have cholesterol. When you hear how many of you have heard the word cholesterol before? If you hear the word cholesterol, you think good or bad? Bad, right? Because we think of it as heart disease and arteriosclerosis, where our arteries harden. But cholesterol is not bad. You need cholesterol. You need it in your diet. Cholesterol is used to help form the cell membrane, to help keep it stable. It's also used to form hormones. Testosterone, progesterone, estrogen are all formed from cholesterol. And it's used for insulation. You might think of an animal that uses fat for insulation. Polar bear? Okay, bears. What else? Seals? Whales? You might know what we call that fat in seals and whales? Blubber. Blubber. It's literally fat that is used for insulation. So now we're going to talk about some specifics about lipids. So lipids, their monomers are fatty acids and glycerol. So what were the monomers of carbohydrates? What do we call them? What were the single units, the simple sugars of carbohydrates? What do we call them? Monosaccharides. So those single units for lipids, we're going to call them fatty acids and glycerol. There's 2 different types of monomers. And this is showing you pictures of fatty acids. And basically what a fatty acid is it has an oxygen, carbon, and a whole bunch of carbons attached to it. And on those carbons, we see a bunch of hydrogens attached to it. forget, start studying, we'll pick up here
Remember to
tomorrow.
maintain clean hands and wear
Y'all have
masks.
a great afternoon.
Do you mind if I take that, those tests tomorrow?
Just show up and remind me.